Hi guys, happy Monday. Today you guys are going to watch this video and we are going to start section 8.6. We will finish it tomorrow. Homework will not be due until Thursday. So to start, if you guys would please take out Exploration 8.6a. We are going to learn some new properties or new identities, sine, cosine, and tangent. If at any point during the video you need a minute to get out your stuff or write something down, please just pause the video so everybody can get caught up. Alright, so Exploration 8.6a, the first thing that we're going to write down is just a quick review on these argument properties. So I learned these a while back and we're going to use them today. And so remember the cosine of a sum of two angles, so the cosine of a plus b, we could rewrite as cosine of the first angle times cosine of the second angle minus sine of the first angle, sine of the second angle. The sine property, when we add two angles, was sine of the first, cosine of the second, plus cosine of the first angle, sine of the second. And we're going to use this fact today to help us find the double angle properties. And so I want to know the property or the identity for sine of twice of an angle. And I'm going to find this by splitting up that theta into a theta plus theta. So I'm going to start with a sine of 2 theta. I can rewrite that as the sine of theta plus theta. And I'm going to follow this sum property to see what this will end up equaling. So I'm going to rewrite it as sine of the first angle, which is theta, cosine of the second angle, theta, plus cosine of the first angle and sine of the second angle. Well, hopefully you notice that at this point these terms are exactly the same thing. A cosine of theta, a sine of theta, a cosine of theta, and a sine of theta. So since these are like terms, I have two of them, so I can rewrite this as 2 sine theta, cosine theta. And it does not matter which trig function comes first. This is the double angle property for sine. We're going to do the same thing now and discover the one for cosine of 2 theta. And so again, I'm going to start with cosine of 2 theta, and we can be tricky and split that apart into theta plus theta. And again, that allows me to use the identity that we've already learned. So I'm going to take cosine of the first angle, cosine of the second, minus sine of the first angle, sine of the second. Well, we know that cosine times cosine is cosine squared of theta, minus sine times sine, which is sine squared of theta. This is an identity for the cosine of twice of an angle. Cosine squared minus sine squared. Now, we learned a couple chapters ago that anytime you see a trig function squared, that there's probably a Pythagorean identity that goes with it. And there is one for sine squared and cosine squared. So remember that sine squared plus cosine squared will always equal 1. And then we could arrange this around and subtract over the sine squared or subtract over the cosine squared. Well, since these guys are related to a Pythagorean identity, we can rewrite this identity for cosine in 2 more ways. So we just found that the cosine of 2 theta equals cosine squared minus sine squared. So to come up with another identity, I can replace the cosine squared with a 1 minus sine squared. And I think I did these in the wrong spots. This was asking for cosine alone, so we'll just swap these two around, not a big deal. So I made this substitution for cosine squared as 1 minus sine squared. Well, now I can combine these two negative sine squareds, and I get 1 minus 2 sine squared. That's another identity for cosine of twice an angle. And again, this was supposed to be down here. So we're just swapping them around. I'm going to do the same thing. I'm going to start with this double angle formula for cosine. Cosine squared minus sine squared. And I can manipulate it in the same way But now, leaving this cosine squared alone, I can replace this sine squared with a 1 minus cosine squared. And again, these are coming from this Pythagorean identity down here. So I'm subtracting a negative cosine squared, which actually makes it a positive cosine squared. And so I end up getting 2 cosine squareds minus 1. And that is another identity. So one way that we could verify each of these identities to see if we were correct is we could graph sine of 2 theta, and we could compare that to the graph of 2 sine times cosine. And so that's what I have over here, y1 sine of 2x. The next one is 2 sine times cosine. And if you look at the graph, this red graph went right over the top of the blue one, which means that these are equivalent to one another. So to summarize, and we're not going to discover the tangent one, that one I'm just going to give to you. And so on the back of your unit circles, go ahead and pause the video on this slide. We're going to put in all of the double angle identities that we just discovered. Cosine double angle has 3 different ones. Sine has just 1. And then this is the one for tangent. So go ahead and pause me at this point, and you can copy these to the back of your unit circle, labeling them double angle identities. Okay, so now that we have those identities discovered and on our unit circle, we're going to see how we use them. And so a common theme is we keep learning new ways to rewrite trig functions, and our reason for rewriting trig functions is to be able to solve equations easier. And so we are going to solve the equation cosine of 2 theta plus cosine of theta, and we're going to find where that equals 1. And as always, we've looked at a graph of the left side, and so you can see that that's this purple graph right here, and I'm looking for where that is going to equal positive 1. We are looking for answers between negative 100 and 850, and so I can see that I'm going to have 1, 2, 3, 4, 5, 6 answers. Since these angles are different in this cosine equation, we're not going to be able to combine these cosines, since they are not like terms. But we did just figure out how we could rewrite the cosine of 2 theta. And we do have a few options. And so looking at our identities, we're going to want to pick the smartest one. I'm not going to replace it with a cosine squared minus sine squared, because then I have 2 different trig functions in my equation. That's not going to help us. Same argument is applied to the 1 minus 2 sine squared. I'm going to end up with a sine and a cosine in my equation if I use this identity. So I'm going to replace it with 2 cosine squared minus 1. So instead of this cosine 2 theta, I'm going to replace it with a 2 cosine squared of theta minus 1 plus cosine theta, oops, messed up there, equal to 1. So now, hopefully you're recognizing that we've solved equations similar to this. It looks like a quadratic, so I'm going to get everything to one side and rearrange it as 2 cosine squared plus cosine. And if I subtract over this 1 and combine it with this negative 1, I'll have negative 2 equals 0. So I'm going to come down here real quick, and we can think of it as a quadratic. And so I will have this as 2x squared plus x minus 2 equal to 0. You could try and factor this all that you want, but it's not going to be factorable. And so whenever we found that a quadratic wasn't factorable, we used the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that gave me my x values. Well, keep in mind, these aren't x's, these are cosine of thetas. And so I'm going to use the quadratic formula and then set cosine of theta equal to the answers that I find. And so my a is going to be this 2, my b is going to be this 1 out front of the cosine, and my c is going to be negative 2. So I'm going to set it up, and I'm going to write cosine of theta equals negative 1 plus or minus the square root. So remember, that's a negative b plus or minus the square root of b squared, so 1 squared minus 4 times a times c all over 2a. So cosine of theta will equal negative 1 plus or minus. Underneath the radical, we called that a discriminant. I will have a 1 here. Negative 4 times 2 is negative 8 times negative 2 is 16. So I'm going to end up taking a 1 plus a 16, which will give me the square root of 17 all over 4. From here, we can use these answers to find where cosine needs to be equal to these numbers here. So I'm going to type this into my calculator. We're going to get some ugly numbers. And so when I take negative 1 plus the square root of 17 over 4, that's going to be my first answer. So negative 1 plus the square root of 17. I'm going to hit enter there. Hope I had an extra parenthesis. I'm going to grab that. I'll start over. So we will have negative 1 plus the square root of 17, and I'm going to take that answer and divide it by 4. And as promised, we're going to get an ugly answer. So cosine needs to be approximately equal to 0.78078, we'll say. I'm going to do the same thing, but now subtract the square root of 17. And then divide that by 4. And we will get negative 1.28, yada, yada, yada. So that's the other value that cosine would have to equal. Now, hopefully you're thinking to yourself that cosine can never be larger than 1. And so this result from the quadratic formula is not going to give us any answers for theta. And so we can just cross that off. So now from here, this is my result. I know that if cosine equals 0.7807, if we were to plug this value in for cosine, that it would make this equation equal to 0, or make this equation equal to 1. So now I need to find all of the angles where cosine has a positive 0.78 ratio. Well, I know cosine is positive in the first quadrant and in the fourth quadrant, so I'm going to take the cosine inverse of 0.78078, that entire number in my calculator. So in degree mode, cosine inverse, and again, grab that entire answer that you have in your calculator, and we end up getting 38.668 degrees roughly. So 38.668 degrees. Well, we know with cosine, since it's an even function, if this is an answer, another answer will be negative 38.668 degrees. And so now that I have my two starting points, we know that we can add and subtract multiples of 360 to get more answers. So this negative 38.668 is this square solution right here. And the positive 38.668 is going to be this circle solution right here. So I'm going to take this and add 360, and I get 398, that's this one, and add 360 one more time, and that's going to give me the 758, that's this guy here. I'm now going to go through and grab the negative 38 degree angle, and we will add 360. That gives me this value right here, 321.3317, yada yada. I'm going to add 360 one more time, and I'm going to get this solution right here, the 681. So that is all 6 of my answers. If you were going to write this out, we would have a negative 38.668, a positive 38.668. We ended up with a then 321.332. We also had 398.668. Then our last two answers, 681.332. And then our last answer, 758.668. So if you need to pause the video at this point and talk about how we got these answers, I know quadratic formula is the new part. When we used to be able to factor, now we had to use quadratic formula. We take the zeros or the answers from there. Now that gives us an idea of where to search for angles.